All right, welcome back to my home office where I'm trying to strike the balance between talking loud enough that you can hear me clearly and not talking so loud that it disturbs my 8-year-old watching Henry Danger in the next room and makes him turn the volume up even louder than it already is. So, last time we were talking about the beginning of quantum mechanics and the first quantum theory, which is Max Planck introducing this idea of a characteristic energy associated with the oscillators that emit light that is proportional to the frequency. So if you double the frequency, you double the characteristic energy. This fixes the problem he was having explaining the blackbody spectrum by cutting off the really short wavelengths, by saying that if you allot energy equally to all of the frequencies that a hot object might emit, then there will be some frequencies, some very short wavelengths, very high frequencies, for which this characteristic energy is just so big that it can't emit even 1 unit. The energy that it would get from the thermal energy is not enough to emit even 1 unit of energy. That gets you the observed spectrum of a blackbody radiation, of the radiation emitted by hot objects, right, which has a single broad peak that moves to shorter wavelengths as you increase the temperature. Makes Planck very famous. Planck was never happy with this. But we've ended up having to accept this, and the reason why comes out of a completely different experiment that was interestingly discovered entirely by accident. This happened during the course of experiments where Heinrich Hertz, a great German experimental physicist, was demonstrating that light is, in fact, an electromagnetic wave. What Hertz was doing was he had a little loop with a gap in it, and he put a really high voltage oscillation on that loop. So the current went slamming back and forth through this loop, and when it come to the gap, it was a high enough voltage that the air would break down and a little spark would jump. That spark amounted to current flowing back and forth. That current was oscillating back and forth as the high voltage oscillated back and forth, and thus producing an electromagnetic wave. Then he had a detector that he put some distance away, and that detector was another one of these little gaps. So as this electromagnetic wave would come along, it would make current try to flow in this loop, but there's a gap, right? So if the gap was large and the wave was relatively small, then the voltage that the wave coming in induced across that gap wasn't big enough to make a spark, and nothing would happen. But if he squeezed the gap closer together, so it was a much smaller distance, then at some point there would be a spark jumping across that gap. He could see the light from the spark, and that would tell him that, aha, I've detected a wave. And the strength of the wave depended on the size of the gap, right? If he had to go to a very, very small gap, that meant the wave was very weak. If he could see sparks jump across a big gap, then that meant that the wave was very strong. This allowed him to map out the strength of the wave at various positions in the lab, and he could show that in fact, the light that he was producing behaved exactly like an electromagnetic wave, as predicted by Maxwell's equations of electromagnetism. So what's the point of this? Well, Hertz, in the course of doing these experiments, was a very careful experimenter, and he noticed that the size of the gap that he could see a spark jump across changed depending on whether there was a line of sight from the original spark to his detector. So if light from the sparks in the original detector reached the detector gap, right, and so his original oscillator is producing sparks that made the waves, if light from that spark was falling on the gap that he was using as his detector, he found that he could get sparks to jump across a bigger gap. That meant that something about that light was making it easier for electrons to come out of the metal and jump across the gap. Now, for Hertz, this was very much a side issue, and so he just made a note of it and moved on. He might have come back to study it later, but he tragically died very young of a rare disease, and so was never able to get back to it. But some of his assistants picked this up, and it picked up the name photoelectric effect. Because, photo, you have light come in, and electric, that light falling on the metal makes electrons come out of the metal more easily. Right? And this is a phenomenon that seemed worth studying. Now, if you're thinking about this in terms of light as an electromagnetic wave, there's a very simple model here, right? You have electrons that are stuck into atoms in some way. A wave comes along and interacts with that, and that wave is going to take those electrons, it's going to shake them back and forth, right? As the electrons are shaking shaking back and forth due to the wave, right, they're going to gain some energy. Sort of like if you're, pushing a kid on a swing, the swings get larger and larger and larger, and they gain energy. So those atoms should pick up some energy, absorb energy from that wave, right? And eventually, when they absorb enough energy, an electron goes pop and goes flying off out of the sample. Right, so this is the conceptual model that people have of the photoelectric effect. It's a light wave coming in, shaking electrons in the atom, right? And you shake those electrons in the atom, and they absorb some of that energy, and eventually they get enough energy that, boom, electron goes flying out. Okay. Now, if we want to look at this experimentally, what can we change? Well, there's two things we can change about the wave. Right? We can change the intensity of the wave. We can make the wave bigger, which corresponds to shaking it harder. Right, I can have a little wave that's shaking it very gently, or I can have a big wave that's shaking the electrons very, very hard. Right, and so a higher intensity of light means shaking the electrons harder. Okay. The other thing I could easily change is I can change the color of the light. Right, I can change the frequency of the light or the wavelength, and what that corresponds to is if I make the frequency higher, then I'm shaking it faster. Right, I'm going the same amount as at low frequency, but I'm just doing it faster. Okay. These are two parameters that we can easily change about the light that we shine onto a piece of metal to study the photoelectric effect. So those are the two knobs that we have as experimentalists. Okay, so what can we measure? Well, there's two ideal experiments you can do using the photoelectric effect, and they both use essentially the same apparatus. You take two plates of metal, place them close together, right, and you shine light on one of them. All right. And the first experiment you could do is you can take those two plates of metal, shine light on one of them, and just connect them with a current meter. What that does is electrons that come out of the bottom plate, well, they'll move up to the top plate and get there, but now you've taken some electrons away from the bottom. Current wants to flow to bring those back. You're putting electrons in the top. They don't want to be there, so they're going to flow through that current meter back to the bottom plate. This gives you a way of measuring how many electrons per second come out of the plate due to the light that you're shining on it. Right. That's the first simple experiment you could do. You can measure how many electrons per second are emitted due to the radiation that you're shining in. The second idealized experiment you could do is the exact same apparatus, but instead of a current meter, you put a voltage meter. All right, and a voltage meter, the distinguishing feature of that is it does not allow any current to flow. So any electrons that make it to the top plate get stuck there. Well, what does that mean? That means that as the light comes in, it knocks some electrons loose. Those electrons move up to the top plate and they get stuck. Then the next electron coming out, as it heads up to the top plate, sees, hey, there's some extra electrons there, and it feels a force pushing it away, right? Because like charges repel each other. As you get more and more electrons collecting on that top plate, the force that the next electron coming out feels pushing it back gets bigger and bigger, and eventually you get to a point where there's so many electrons on the top plate that the next electron coming out at the bottom says, nah, I'm not going there, right? And turns around and goes back. At that point, you stop getting any more electrons coming out, and you've developed some voltage between those plates. Right. That voltage is something that you can convert directly to an energy. And so connecting these plates with a current meter tells you how many electrons per second are coming out. Connecting the plates with a voltmeter tells you, how big an energy difference can you generate between these plates. Tells you what is the maximum energy of the electrons as they come out. So this is a nice, simple experimental situation. Right? We have two things we can vary, and we have two experiments that we can do to look at. So there's sort of four questions we have to answer. One is, if I change the intensity of the wave, right, how does that affect the number of electrons per second that come out? And then I can ask, if I change the intensity of the wave, how does that change the energy of the electrons that come out? If I change the frequency of the wave, how does that affect the number of electrons that come out? And if I change the frequency of the wave, how does that affect the energy of the electrons that come out? Right, I've got two parameters I can vary. I've got two experiments I can do to make measurements. That's a total of four possibilities. Those four things are predictions you ought to be able to make using this wave model of a wave that comes in, shakes electrons back and forth, deposits some energy, and once there's enough energy, an electron pops out and leaves the system. This is a very straightforward sort of situation, right? This is something that model, you ought to be able to intuitively make some predictions about these 4 cases, what you think will happen in those 4 cases. So do that. The next assignment for you on Nexus is going to be a quiz with some text boxes where we want you to write down predictions for what's going to happen in each of those 4 cases. How does the number of electrons per second depend on the intensity? How does the number depend on the frequency? How does the number depend on the, how does the energy depend on the intensity? And how does the energy depend on the frequency, right? The quiz will ask you to write down predictions of those 4 things. Once you've submitted the quiz with those predictions, and you're not being graded on whether you guess right or wrong, so don't go Googling this to find out what the answer should be. What I want on the quiz is just your intuitive understanding of what do you think is going to happen based on this wave model of light and in these 4 situations. Okay, so you're going to write down those predictions on the quiz. Once you've submitted that will unlock another video where I talk about what the predictions should have been, right? What people actually thought was going to happen, and then that will unlock an activity where you're going to go and look at some fake data from these 4 experiments and see, does what happens actually correspond to what we predict, and that is how science works. So, which is the whole point of this class, for you to get a little experience looking at how science is actually done. So think about that model of waves shaking electrons, accumulating energy, eventually knocking an electron loose. Think about those 4 combinations of experiment and varying parameter. Make your predictions, and we will see you back here for the next video.